Okay, so everything that I'm going to do today, except if you ask me new questions, but all of the stuff that I'm planning to do today is in the files that I sent out by email and that are posted on Blackboard and on the wiki. So you should be able to close your laptops and just follow along. And in the files that I sent you, there's one file called exampleplot.pdf. Which shows you a little bit of kind of where we're headed. So we're going to load a data file that is going to have the firing rate of neurons as a function of time for many neurons. And our little mini project for today is to plot the firing rate as a function of time for each of the neurons. So each of these traces is one neuron. This particular data file had 50 neurons. And we don't want to plot them all directly on top of each other. We want to spread them out a little bit vertically so that we can see the different traces. If we plotted these 50 traces, those 50 traces that you see up here, if we plotted them just with the same baseline, they'd all mush up and you wouldn't be able to see anything. So we're spreading them out vertically so that you can see them. And then something that, say a typical thing that you might want to know is if you have a bunch of neurons that you've recorded from, what's the average firing rate across all of the neurons as a function of time? And so that's what we want to plot down here. This is going to be the average across all of the neurons at each time point. And whenever you look at different averages, say that we look at the different time points, you might wonder, are these significantly different to each other? So let's plot not only the mean across all of the neurons, but also plus minus the standard deviation across those neurons for each time point, and we're going to do that across all the time points, right? So this is taking the average and the mean across neurons. So that is, sorry, the average and the standard deviation across neurons vertically in the matrix that has all the information that is shown here. And you could also ask, for each neuron, averaged across time, what is its average firing rate, and what is the standard deviation of that? And that's what we're going to plot over here. So each entry here is going to be, for say this is for neuron 50, what its average firing rate was, and plus minus the standard deviation of what you see across time. So the original data comes in a matrix that has the same number of rows as there are neurons, and the same number of columns as there are time points. And we're going to have a time vector that will tell us, how to index those time points. That's our original data, and from that original data, we want to produce a plot like this. Okay? That's where we're headed. And I've kind of schematized this out here so that as we go through it and I take this plot off the screen, you guys have something to help you remember kind of where we're going. Yes? Yes, so this line, so the height of this point, of each of the points at each of the time points, corresponds to the average across neurons of the firing. Those are all. Aha. So each of the neurons, that corresponds to the vertical displacement that we're doing just to plot the neurons differently. Okay. So let me load up the data and first plot them all on together where they all have the same baseline. And then we're going to work on displacing them so that we can see them all. Okay. So great question. Let's load up the data. So the particular data here is in a file called firing rate data.jld. So let's load it up. And we've got one time vector, and we've got 3 examples of matrices like what I described, where each of these matrices, FR1, FR2, FR3, has number of neurons for the rows, and the number of columns is as many elements as there are in T, the time points. So let me put that in some variables that makes it easy to type and work with. So here's our time vector. And if I asked how many time points do we have 81 different time points. And let's say that our data matrix, let's call it D for short. Let's say that we start with FR1. Okay. Or actually, why don't I call it FR1 just to remember which one it is. Okay. And let's ask what's the size of this. So remember I told you that the number of rows is the number of neurons, so we've got 50 neurons. And we've got 81 time points corresponding to this length. Yeah?
Why did you put the semicolon after
Oh, the semicolon just means don't spit any result out.
Okay.
So if I don't put the semicolon, it just does that, and it just so happened that I didn't want to fill up the screen. Okay, so now we've got our matrix. Let's look and see what's the kind of thing that we would like to plot. Oh, let me run this. This is just the magic to make the defaults a little nice. So the size of the font and stuff like that. Maybe I'll do it a little bigger so you can see it a little better. And I want to emphasize everything that I'm going to type into the editor here is already in the files that you already have. Okay? You don't have to copy from the screen. Okay. So say that we wanted to plot the first neuron's firing rate as a function of time. We said that each neuron is one of the rows of that matrix. So if we wanted to plot the first neuron, we might choose the first row. And you guys will remember that for matrices, you index into them by whatever goes before the comma is the row, whatever goes after the comma is the columns, and here we're asking for all columns. Okay. And we had 81 columns, and we had 81 elements in T, so we can plot these two against each other. That's the first neuron's firing rate as a function of time. Now let's plot them all. So we could loop over the number of rows in FR1, just go over all of them. And each time that we're doing that, we're going to add something to the plot. So the number of rows in FR1 is the first element of what we get from this size command. So this will loop over the number of rows. And for each one of them, we want to do kind of exactly what we did just now. We want to plot it. But this time, we're going to ask for the ith row. Right? And that's how we loop over all the rows and get all the rows. And because we want to add to the plot, we don't want each new neuron to replace the previous one. We want to add them all together. We do it with the exclamation mark. Right? And so that's going to mean add to the plot. And now we type the end so that to let the loop go. And I'm just going to press return to go ahead with that. People were asking about plotting. Here's an example of plotting. I don't know if this is enough or you wanted more information or this helps. OK, good. There was a question here and then a question there.
Usually we use length. But in this one we use
size. The thing is that FR1 is a matrix. So length of FR1, so that means that we have both number of rows and number of columns. So if you ask for the length, what should it give you? The number of rows or the number of columns? Length will actually give you the total number of elements in FR1. So length of FR1 is going to give you the number of rows times the number of columns. That's the total number of entries in the matrix. Size does distinguish between rows and columns. So let me click return since I've already typed this. Okay. And I want to make sure to tell the system, hey, whatever you've sent to the plot, make sure to show it. Okay, so there are all the neurons overlaid. Okay, question there and then a question there.
So for font, is that part of some kind of package?
This is part of the plots package. So when we start plots using this, that means that these commands are used. And
sorry, going back to the size thing, since size of FR1 will return like a vector, right? So if you wanted the number of, so what does the comma one mean?
Excellent question. So here's the part of the answer to your question, right? Size returns number of rows and number of columns. And suppose that we only want the first one. One way to access that would be to say, just give me the first element of whatever size return. That's going to be the number of rows. Or you could say, give me the second. And probably I should have written it like that for simplicity. It turns out that when they wrote this size command, they also said, oh, if you add another argument to tell me which of the two you want, I'll give you that one. Okay? So this is exactly equivalent to that. So it's just another way of saying, give me the first thing, which is the number of rows. And similarly, we could use size to ask for the number of columns like that. Okay, so we plotted them all. we went through this loop where on each iteration of the loop we added a neuron. And now here we have all the neurons. And this was partly in response to the question of like, wait, but what average are you looking at? And what you can see here is that if we plot them all just directly on top of each other, you can't tell one from the other, right? Because there's so many that you can't tell what's going on. So what we want to do here is not to plot them all with the same baseline. But plotting each neuron, displace it a little bit vertically so that we can see them all. So for example, let's do a couple of neurons. Let's just do them by hand. And when I say by hand, what I mean is I'll do it here on the console before we write it. So I call plot with something empty to clear the plot. And let's plot the first neuron. Plot it like that. And now let's say that we want to plot the second neuron, but we want to start it from a little bit higher. So, I don't know, we could start it at 50. And then when that neuron's firing rate is 0, it would start here. So, and let me remember to add the exclamation mark to say I want to add something to the plot. So now you can see that there's 2 of them, right? Because I separated them vertically. So that's what I want to do. I want to see all 50 neurons separated vertically. And that's what we're seeing. When we compute the average and the standard deviation for that bottom part of the plot, for this one, I'm going to ignore that vertical separation. That vertical separation was just for display purposes, right? The average will be the average of the original. So let's say that we're going to set out to do that. How might we do that? So let's write a function. In fact, maybe I'll start with a script and then we'll turn it into a function. So I clear the plot, and then I'm going to go over the number of rows of FR1. And this time I'll do it with this notation. Right, so that just says loop over all the rows. And now I want to write down a plot command that is very similar to what we did here. So I want to plot something versus time. Each time that we go through the loop, I want to pick out the ith row so that we do all the neurons as I loops through all the neurons. And then I want to add something here. How much should I add? What could I do here? So say that I had 3 neurons to plot. Let's go back over here. Let's say that now we're going to plot a 3rd neuron. What could I use for this number that would separate it vertically from the 2 that are already on the screen? Any suggestion? Any old number? 100? I heard 100, 200. Let's say that we use 100. Whoever said 100, why did he choose 100?
I don't know if we're going up by an increment of 50, so I'll just put
Let's say that we decided to go by 50, right? So then the 3rd one would be 100, and the 4th one, how much would the 4th one be? 150, and so on and so forth. Right? And you can see them all, they're separated. So let's do that. Let's just encode that up here in the program. So what could I write here that would give me a behavior similar to that? Yes?
possibly 50 times I.
50 times I. Why not? And then every time that we go through the loop, I is growing by 1. So every time that we go through a loop, this is going to grow by 50, and we should get them displaced by 50. Sounds excellent to me. Let's try it out. Oh, and I always forget to write this, which says, show me what you got. So let's try that. And there it is. You can actually kind of see them all. Say that we hadn't started with 50. Say that we had started with I, with separating them just by 1. If we do that, it's kind of a mess. Okay, so maybe 10. Maybe they're still a bit of a mess. And how much we should separate them by depends on the scale of each one, right? So we're doing a bunch of traces. each of which looks like something. And how far up higher the next trace should go so that we can separate them a little bit depends on this height, the difference between the maximum and the minimum. So what I'm going to suggest that we do is that we rescale each one to go from 0 to 1. And then we know, for example, oh, we can separate them by 1. Or we can do something that if somebody comes along with another matrix where the firing rates, instead of going, say that in FR1 they go from 0 to 20, what if somebody gives you another matrix where the firing rates go from 0 to 1,000? You'd like to be able to use the same code to see them. So we have to scale our plot to the scale of the data. So to do that, what I'd like to do is write a function that will take a vector. So remember, these are represented as vectors, so there's a finite number of them. In fact, there's 81 time points, so this is a vector 81 long. And what I wanted to do is rescale that vector so that the minimum value now becomes 0, and the maximum value now becomes 1. And that's a way of standardizing. Whatever we get, we're going to standardize. So let's write a function that does that. And we're going to use it to improve our plotting, our trace plotting function. This double hashtag symbol separates cells in the file. And so what it means is that when I press Alt-Enter, only what's within the current double hashtag gets executed. So it's a way for me to separate things as we go. So I want to write a function, let's call it rescale, where you give it a vector. And let's make it pretty general. We're going to tell it the minimum and the maximum. And what I wanted to do is whatever is in that vector, rescale it so that whatever was the minimum value of x now becomes mn, and whatever was the maximum value of x now becomes mx. mn for minimum, mn for desired minimum, mx for desired maximum. How could I write that? Well, among other things, we need to know what the minimum value in x is, right? And we need to know what the maximum value in x is. But, sorry, no buts yet. As it turns out, Julia has a function called minimum and a function called maximum that will compute that for you. But for the sake of just writing functions ourselves and going through that, let's write a function that does that. Let's write two functions that do that. And what I'm trying to do now is go through an example of, we had a big problem that we're breaking down into smaller problems. We had this big problem of, how do we plot multiple things and scale them automatically so they don't overlap too much with each other, no matter how much they are. Well, to do that, I need to scale, hey, let me work on the scaling problem for a little bit, just on the scaling, right? And in this function, I'm not worried about plotting, I'm just worried about scaling a vector, right? So I'm taking one small chunk of the problem. And then we thought, oh, for scaling, you need to know the minimum of the vector and the maximum of the vector. Okay, let me write that. And I'm going to write a function that just does that, right? So I'm taking an even smaller chunk of the problem. And as I write a function for these small chunks, I can debug each small chunk. And by separating it out into a small piece, it becomes easier to think about and easier to debug. So for example, finding the minimum of a vector, we can totally do that, right? Scaling, the auto-scaling, that seems more complicated. We'll build the tools to make that a little easier for us. Okay, so let's write a function that, given x, returns the minimum of x. Okay. And document. In the file that I sent you guys, everything is documented. Okay, what should I write here? Some suggestions from the audience, please. So let's see, who are the people with the least programming experience? Okay, that's not a question that you can ask, that you can answer without comparing yourself to each other. Those of you that have not taken a programming course before, please raise your hands. Thank you. So I'll start at the front. Give me a suggestion for what I could write. I want to find the minimum. So say I've got a vector. let's say I've got this vector and that x is 3, 5, 1, 7. You know, it could be anything.
Would you order it and take the first? To find out what the minimum is? Does that make sense?
Well, let's walk through logically, kind of like what do we need to do this, right? Let's think logically about what we want the computer to do, and then we can figure out, okay, what do I need to write to get the computer to do what I want? And what I'm trying to ask right now is, what would you like me to do? If you were telling me how to find the minimum in this vector, and these values were actually hidden, you don't know what they are. You want me to tell you which of them is the smallest one. How would I go through? There's a suggestion at the back.
You want to look at one number and compare it to the next, and that one's smaller, and keep that one.
So we're going to go through, we're going to go through each of them, asking, are you the smallest one that I found so far? If you are, then you're my answer. If you're not, I'll ignore you, and we keep going, and that way we loop through all of them until we've got the very smallest one. So what could I write here to do that, right? That's, in English, what we want to do. What should I write here to do that? You've already asked a question. Somebody else. I'm going to pick on you leaning on your hand just to try and distract you a little bit.
You could do, or I do like, or I would want to do like the x, and then do if x of 1 is bigger than x of 5, and then we need to create like an answer.
Yeah, let's create an answer variable. What could our first guess for the answer be?
X of 1.
Sure, right? We got to pick one thing, right? So let's say that our first guess for the answer for the smallest one is x of 1. So then we've done x of 1. Let's start at x of 2. And now what is it that we want to ask? Yes?
Oh, I was gonna ask, is there a variable in Julia where it's like positive infinity or like negative infinity?
I think there is, although I forget. Yes?
Okay.
Okay, back to what we're writing here. Somebody help me out with this loop. Right? So we've made a provisional guess. Right? You said this. I'm guessing that this is the smallest one. Now we're going to loop through all of the others. When I'm considering this one, what should I ask? In order to, maybe this one is the smallest one, right? I want to figure that out. What should I ask? To see, compared to my current guess, what do I need to ask to see if it's the smallest one? So I need to ask something about x of I. Yes?
You want to ask if it's less than your answer.
Okay, and if it's less than my current answer, what do I do?
You want to update x of I as your answer.
Right, so now I'll say, oh, if you're smaller than what I thought was the smallest one, then my guess for the smallest one is actually the current one. And I just keep looping until I get to the end, and then I'll have looked through all of them. So that sounds perfectly reasonable, and we've written the function. So when I type Alt-Enter now, it evaluates it. So now we have a function. Our function mymin now exists, I think. Yeah, here it is. That's the documentation that we wrote. Let's debug this. Right? So anytime you write a little chunk for something simple, debug it, test it with the simplest thing, with simple things. And then once you're confident that it works, that's it, right? You can then use it, and you don't have to be worrying about, oh, is there something wrong with that, right? Because you're building up bigger and bigger chunks of code. The smaller the chunk that you debug and test, the easier it is to think about. This is a pretty small chunk, and hopefully easy to debug. So, let's try it with some vector. Is it going to give us the smallest value? No, it gave us nothing. That was disappointing. So I unintentionally goofed. I forgot something. Yes?
Never told us to return anything.
And now we told it to return anything, so it didn't return anything. So what should it return? Yeah, right. Once we finish the looping, that's what it should return. Let's try again. Okay, it says that the smallest one out of all of these is 1. Sounds good. In the example that we just tried, 1 was also the very first thing, right? So let's put it somewhere in the middle instead of. And what if we now change this to 1,000? Yeah, now the smallest one out of all of these is 2. Looks like it works. Okay. Great thing that we just did. We took a little chunk of the problem. We got something that solves it. Now we're confident that mymin works. We're not going to look at it again. Now we wanted to do the scaling. We wanted to figure out what the smallest value in a vector was and what the largest value in the vector was. So we could do the rescaling. So we'd like a function, let's call it mymax, that returns the maximum. So, you know, it's likely to look a lot like mymin. So I'm going to copy mymin. I'm going to call it mymax. Returns its maximum. And what should I change? Yeah, right. Now we're asking, is the current guess, or is the current element that I'm examining bigger than my guess? If so, then my guess should be that. Okay, so is that true? Let's test it. You know, once again, something I often fail to do is I write a little code, and then I forget to test it, and then, you know, 3 layers away, it turns out that I forgot to do something in the code, and it's just a pain to debug. If you test right away, then you can be confident that it works. So this should return 1,000. That is the largest one of those. What if we make this smaller? Returns 900.3. Okay, looks like it works. Now let's do this thing of rescaling a vector. So what do I mean by rescaling the vector? So say that you've got a vector 1, 3, 5, 2. And let's say that I want to rescale it so that its new minimum is 0 and its maximum is 1. What I mean is that we want to subtract something from every element in the vector, and we want to multiply everything in the vector, such that after doing that, the smallest one will now be 0, the largest one will now be 1, and everything in between will be scaled corresponding. So how might I do that? Again, not in Julia yet, just kind of like in English and kind of logical speak. Suppose that I want to turn the smallest one into 0. What could I do to my vector? Is there something that I could multiply the vector by, or something, a number that I could subtract from the vector, or add to the vector that will make sure that the smallest element in the vector is 0?
Once you find what the minimum is, you subtract the minimum value of each.
That sounded nice to me. Oh, I've got this vector. Why don't I, instead of writing out a vector 20 times, let's use this as our test vector. Why not? Okay, here's our guy. And the suggestion was, let's take the vector and subtract the minimum. Yes?
Wait, don't you want the maximum to be 1 though? So
I do. I want the minimum to become 0, and I want the maximum to become 1. So I'm going to have to do 2 things. Subtracting is not going to finish the story, but it's just the start of the story. So if we subtract the minimum, well, the one that was the smallest, we subtracted 2, so of course that becomes 0. Right? And everything else just got subtracted along with it. And now I want the maximum to become 1. So how could I make the maximum become 1? If I'm adding, subtracting, multiplying, or dividing. Those are the, by scaling, I mean a linear scaling, so I'm allowed these linear operations. Wait, you already answered one thing.
Divide the maximum.
Divide by the maximum. Sounds like a good plan. So divide by max of x. Okay. Oh, I guess x is too long Wait, let me do a smaller x just so we can see them all on the screen. So let's say that do that. Okay. Well, that didn't quite work, right? We got 0.997. We should have gotten 1 exactly. Yes. Right. So we had subtracted the minimum here, and what we wanted to do was divide by the maximum of this vector, not of the original. Right? Does that make sense? So let's look at this. Right. We had this guy. Right. This is the one where the minimum had become 0. And now to turn the largest element of this into 1, we want to divide by whatever is the largest element here. So we could write that like this. Divide by the largest element in x minus my min of x, right? That says take this and now divide by whatever is its largest element. And now the largest one is exactly 1, the smallest one is exactly 0. That worked great. We could also have written it like this. And those are the same thing, right? If we look at the original, this difference is the same as what we had in the previous one. Okay, so now we know how to scale a vector into into something that lies between 0 and 1. But what if we decide that we want it to lie between 3 and 4? Or let me do 3 and 5. So I want the minimum to turn into 3, and I want the maximum to turn into 5. Any suggestions? Let me do it instead. We'd scaled it between 0 and 1. Let's keep the minimum at 0, and now let's turn the maximum into 2. Instead of scaling it between 0 and 1, I want to scale it between 0 and 2. Here's this expression, this Juliet code, that turns into something where the minimum is 0 and the maximum is 1. What could we do to this guy to now make the maximum 2? Multiply by 2. That makes sense, right? Because the minimum is 0, so when we multiply by something, that's not going to change. Yeah, so now the maximum is 2 and the minimum is 0. And now suppose that we wanted, instead of 0 and 2, that we wanted it to be between 3 and 5. What could we do now? Add 3. Yay, minimum is 3, maximum is 5. So what did we do here? We multiplied by the range that we wanted. We multiplied by the difference between the largest thing that we wanted and the smallest thing that we wanted. And then we added the smallest thing that we wanted. So let's write that in a function. So function rescale of x to some desired minimum and some desired maximum. Actually, do I have this function elsewhere? Oh, yep, I had already written those lines here. Okay. So I'm just going to copy what we had here because we'd already worked that out nicely. Okay. So let's say that our temporary answer is this. In fact, let me take it in steps. Okay, I'll move it. I want to make it so you guys can see all of it. Right? So first, we make the minimum 0. Then we divide by the difference between the maximum and the minimum of the original. So now, answer now the range is 1. Or rather, I'll write it like this. It goes from 0 to 1. Then we're going to multiply times the range that we want. So now it ranges from min to max. Oh, sorry, it ranges from 0 to max minus min. And then we just add the minimum. And that's just going through the steps that we did on the screen. Yeah.
So will it, like I know this could give the correct output, could we also, could we know the size of x? So could we use the size of x to get a fraction of the range and just add that fraction x times to get each element? So you start at the minimum value, and then you take the range of like what you want to scale it to, and then you divide that by the number of elements you have, and then you.
Well, but the number of elements you have isn't telling you anything about what the maximum value or the minimum value of those
But if
elements
you
is.
start with the minimum, and then you distribute that range across each of the elements, you end at the maximum, right?
I'm not sure, when you say distribute that range over the elements you
This
have.
exact example.
Okay.
So you have 4 elements,
Yep.
and your range is 2. So 2 divided into 4 elements gives you 0.5, and then you start at 3, and then you add 0.5 to each element, you end at 5.
Wait, do it again. You're going too fast for me. So I start with this vector.
So I know the size of x is 4,
Okay.
and I know that like the final range I want to end at is 3 to 5, which is 2.
Okay.
And so I divide that range across each element. So 2
When
divided
you
by
say divide that range across each
so
element.
2 divided by 4.
2 divided by 4. I don't think it's going to work because the operations that we're doing don't really depend on the number of elements. Right? If you look at what we did, what we added, what we subtracted, and so on, we would have done exactly the same things if there had been 7 elements in the vector. So what we multiply, what we subtract, is just about the maximum minimum value, not the number of elements in the vector. So that's telling me that whatever procedure incorporates the number of elements isn't going to work. Okay, so we have a putative function rescale. Let's test this. So here's our vector x. Again, the same procedure. You write a function, you test it with something really simple. Let's say that we want it between 0 and 1, kind of like how we said. Minimum is 0, maximum is 1. Okay, let's say that we want it between minus 23 and 15. Minimum is minus 23, maximum is 15. Okay, looks like it works. So now, we went down into smaller and smaller chunks, finding the minimum of a vector, finding the maximum of a vector, rescaling. All of that was in the service of rescaling each of these traces so that we would easily know how to spread them out. If we rescale all of them to lie between 0 and 1, then we know that if we spread them out vertically by 1, it's always going to work, no matter what matrix we have. And you have a question.
Why did we put return at the end of this function?
Oh, because I'm an idiot and I forgot to do it. That's why. Thank you.
It's still working.
Yeah, so Julia, its default is to return whatever the result of the last expression was. And so I got lucky, and it turned out that its return is ans, so it worked, but that was a goof. Okay, so let's use the function rescale to do this plotting thing that we wanted to do. So let's take our matrix, and let's say that our scaled matrix is the rescaled FR1, and let's scale it between 0 and 1. So now every element in FR1 lies between 0 and 1. And so now, we could say, you know what, if I separate them vertically by 1, I know that no matter what the values of FR1 were, it's going to look kind of nice, or roughly. Right? Let's see what that looks like. Ooh, that looks terrible. Oh, that's because I was plotting FR1 instead of S. I wasn't using the thing that we rescaled. So let me try again. Okay, that, looks better. They're a bit tiny. Maybe we want to scale them a little bit more. Maybe we don't mind if there's a little bit of overlap. I don't know, let's scale it, say, between 0 and 2. Oh, oh, let's get ambitious. Let's get it between 0 and 10. Okay, now they overlap even more, right? But the point that I'm trying to do is that by specifying the rescaling, we control how much they overlap no matter what we get. We've made our function a little more robust. Doesn't matter the value that we're getting, it'll show something reasonable. And we haven't yet turned it into a function. So let's call this function, I don't know, something like plot the traces. We need the time vector. We need the matrix. And then other than that, we do kind of exactly what we've done. Okay, so we've defined the function. Let's see, plot plot traces. Does this function work? T of fr1. There they are. How about we do it to fr2? So we could look at fr2, which I haven't yet pulled out into its own variable, but this gives me fr2. In principle, it should work, right? Because we try to write it in a way that no matter what matrix we gave it, it would work. You know, it looks, we managed to see all of them. They're displayed vertically, kind of like what we wanted. Okay, so we've got this part. Now we need to get this part. We're going to do this part first, and then that part. So what we want to do is find the average across the rows for each of the columns. And that's going to give us this thick line, and then plus minus the standard deviation is going to give us the 2 family. Yes?
So, why do you like rescaling the same function at the same matrix every time?
Why am I rescaling? Oh! Thank you. Because I am, again, an idiot. We only need to rescale it once. Thanks very much. So let's just run that again to make sure that it works. Yeah, looks nice. How about fr3? Yeah, seems like it's working. Thank you for that. Okay, so on to this. So again, we want to kind of cut things out. So right now, we've plotted this. We know that we want to plot something else down here. The plotting the two together might be a little complicated. So let's cut out a chunk that we can work on independently of the plotting. Let's just say we want to write a function that, given a matrix, plots the average across the rows plus minus the standard deviation across the rows. And then how we accommodate that with the plot of the individual traces of each row, we'll worry about that later, bit by bit. Right? And again, we'll take this chunk, we'll write that, we'll debug this chunk, and then we'll go back to a different chunk. So new chunk. And let's call this is going to be something that maybe we'll start with a script and then wrap it inside a function that we can call more efficiently. So we've got a matrix. So some data, and there's some rows and some columns, and we would like 2 vectors. One of them, and each of the 2 vectors should have the same number of columns as our original matrix. One of them, let's call it NEU. It should be the average across the rows. And the other one, which here I'm going to call sigma, but in the actual code we want to use Greek letters. I'll go and Julia can, don't mind about that. We want it to be the standard deviation across the rows. So let's write some code that computes that. What should I loop over here? So let's first produce this mu vector. So given a matrix fr1, oops, down here. Given this matrix fr1, how do I get something that is the average? It has, I want a vector that is the same length as there are columns in fr1, and say for element 3, I want it to be the average of all the elements in the 3rd column of fr1. And I want to do that for all of them. Some suggestions, please. You haven't said anything yet, at least today. Take a random guess, it doesn't matter.
Sorry.
So we've got a matrix. This is our matrix fr1. And I want to produce a vector. We'll worry about the standard deviation later. I want to produce a vector where its first element is the average of everything in the first column of FR1. The second element is the average of all the rows in the second column. The third element is the average of everything in the third row, and so on and so forth. Pretend that your entire grade depends on it. You got to try something. You start writing because you got to try something. What would you write? For loop, sure, because we're going to loop over all the elements, right? Okay. Probably a for loop within a for loop. Okay, so what could my first loop be?
1, 2,
So let's say that our first loop is going to be going over these, right? So how many iterations of the loop do we want? It's the number of columns of FR1. Right? That's how many of these we want to do. How do I find out the number of columns in a matrix? So remember, length tells you the total number of elements. It's great for vectors.
use size M, and then the brackets will come with it.
Excellent. Okay, and it always goes rows first, columns second. Exactly. So number 2. Right. So that's our loop. And then within each, so when I equals 1, we'll be doing this guy. When I equals 2, we'll be doing this guy. When I equals 3, we'll be doing this guy. Okay. And within each run of the loop, what do we need to do? So now I want to find the average of all the values in this first column of FR1. You were totally right. We need another loop, right? Keep going, don't stop. You're doing great.
So we want to create like a 4J and size, I for the size of whichever, next one we're going to do.
And what should I write here?
So where is the M on the side?
The M. So,
Second.
oh, this guy. Okay. So this vector, we haven't done anything about that vector yet.
The one we're going to assign.
Yeah, that's where we're going to store the result. So maybe we'd like to declare it just to have it around so that we can put things in there. So let's make it with the zeros command. And how long should it be?
It should be as long as how many columns there are.
Exactly. So columns. Rows first, columns. So that's as long as there are columns. Okay. And here,
Wait, we want to do the second for loop. Bracket one.
and this, thank you. Right, and that bracket 1 tells me that we're doing as many as there are rows. Want to continue, or shall I pick on somebody else? Somebody at the back.
Is there a mean of the whole column?
Say that again.
Can you just do the mean of the whole column?
So it turns out that we're going through this by hand to see how you do a mean, but in fact, it always pays to wonder, does Julia already have a command to do this? And it turns out that Julia does. So yeah, so we could do that. So for example, instead of this inner loop, we could just write mu of I is the mean of FR1. And we wanted the whole row, right? So how do I tell it, say that I want the ith, how do I tell it that I want the ith column? Colon, comma, I. Right? Colon says, give me all the rows, and comma I says, in the ith column. And in fact, it turns out that there's even shorthand for writing this whole loop in a single command. We won't do it right now, but and we also wanted the standard deviation. So let's do that. And this command, std, does not stand for what you might guess it stands. Don't think about that. Is the standard deviation. It will give us the standard deviation of a vector. So if we run this code that we've written right here, now we've got the mean firing rate as a function of time, mean across all the neurons, and we've got the standard deviation of that firing rate as a function of time. And now we'd like to produce a plot that looks like this. And as I said, let's go step by step. We're going to worry about trying to incorporate it into this bigger plot later. For now, I just want this part. So I'm going to clear the plot plane. Goodbye, whatever was there. And so we can plot the mean as a function of time like this. And now we'd like to add those two thin lines for mean plus standard deviation and mean minus standard deviation. So how could we write that? Any guesses as to how we could say it? Now add this thing. Person in the paper side of that haven't made sense.
You could add mu plus S.
Let's try it. Why not? We want to add to the plot, not replace, so we use the exclamation mark. Okay, and let's see what that looks like. Okay, there's the mean plus the standard deviation. How about the mean minus the standard deviation? Tell me what to write. Sounds good to me. Oh, I forgot the exclamation mark. So the last one, line 72, replace the previous plots. Let's add the exclamation mark right here. And there it is. The mean plus minus the standard deviation. Now, in the example plot that we had this like, cute thing where the mean was thick, the standard deviation was thin. It gave this nice feel. So let's do that just because, that's kind of cute. And it turns out that there's this optional line width command that you can use to tell plots what it is they want. So thick line width for the mean, thin for that. Okay, now it looks nice and semi-fancy, like you might see in a journal or something like that. Okay, so let's put this into a function. Right now we wrote it as just a script. Let's put this into a function where it could do it for any matrix that we get. So I'm going to call it plot mean and standard deviation. We need a time vector, right, because that's what is giving us the numbers that we have on the horizontal axis right here. We need some matrix. I'm going to call it A just to emphasize that it doesn't have to be FR1. It could be anything. It's a function that we're declaring. And so we do just the same thing as we had done before. Including the plotting, except that now it's for this matrix A, which is whatever the user, when they call this function, whatever they give us. And let me remember to do the thing that I always forget, which is show me what you got at the end. And so now, if I evaluate that, now we've got this new function, plot mu SD. And we're supposed to be able to give it a time vector and our matrix. And it works. How about, I can't remember, let's pull out a couple of other matrices from the data that we had loaded from the data file, FR2 and FR3, to see if it works for them also. And note one thing that I'm not doing, when I say it works, I'm seeing that it doesn't crash and it does something reasonable, which is not the same as it works. Right? If we were being careful, we'd actually check that the lines are, one standard deviation above and one standard deviation below. Here, we're just going to trust that it is what it claims to be. Okay, so we said we can give it any old matrix. How about we give it, you guys might remember that there's a command, the apostrophe, that flips rows and columns, right? So if we do that, that's a different matrix, right? It just flipped the rows and columns of FR2. So let's try plotting that. Because we said, oh, we can give it any old matrix, right? And it should plot the mean and the standard deviation. What was that? So something that we haven't checked here, there's an assumption in what we wrote, which is that this vector t was as long as there were columns in A. And it's often useful to make sure, if you're assuming that in your code, if you're assuming something in your code, have an if-else statement that checks to see whether that's true in case somebody, when they call the code, goofs about that. Maybe they forgot about that. They don't get some weird behavior or some error that is kind of hard to figure out what it is. So we could put in something that looks like, if the length of t is not equal to the number of columns in A, then we say, no, no. Okay. So let's see if we try this thing again. Oh no, that didn't work at all. What? Okay, now I'm confused as to why that didn't work. Excellent teaching moment. Let's use the debugger to figure out what the heck is going on. I thought that in what we just called the length of t was not equal to the number of columns in A. So I'm going to use the debugger, because I don't know what's happening. If I'm going to use the debugger, I've got to include the file. So rather than doing the thing of having my cursor there and typing Alt-Enter, I need to explicitly include it so that Julia knows exactly where all the line numbers are. And this file that we've been creating is called Lecture 7. Okay. And now let me try this again, but with the @enter command that says go into the debugger. Oh. Huh. Can anybody see what I did wrong? So the debugger took us into the function that we called. Is this the function that we were writing? No, right? So the idiot lecturer, instead of writing plot underscore mu underscore st, which is the function that we wrote, I wrote plot. I forgot the underscore mu underscore st. So no wonder it was giving us some weird behavior. So let's try again, but this time actually calling the function that we wrote, which is called that. And now it gives us an error, and it tells us what the error, what we did wrong. And this plot.jl, that's not something that we want to do. Okay, so now where we are is that we're able to create a plot like this. Now let's try putting this on the bottom of the previous plot. So to do the previous plot, let's say that we're doing it with this matrix FR2. That was the function that we wrote that did that. You guys remember how we scaled everything, and then we separated them vertically so that we could see them nicely. And now we want to add some stuff at the bottom. So how can we do that? What do we need to do to make it come out reasonable? Well, in our plot mean and standard deviation function, we were starting by using plot without an exclamation mark. So the first thing to do is replace that with an exclamation mark, right? So that we don't erase previous things. But let's suppose that we then try it. Let's suppose that we then try to add to our plot by calling our function. Plot's kind of like in the middle of things. So we're going to need to reposition it. We're going to need to tell Julia kind of where we want it. If you were really doing this, say for like a paper that you're writing, probably what you'd want to do is have separate axes for the individual traces and another axis for the mean and the standard deviation. And there are ways in plots to have multiple axes in one figure. But for now, we're doing everything on the one axis, so we have to figure out how to lay this out, essentially. Any suggestions? we already wrote a function that might be very useful to us, which was the rescale function, right? Because the rescale function, what we used it for was to help us put things and scale them in the way that we wanted for the screen. That's kind of what we'd like here too, right? So we'd like to take this mean plus minus the standard deviation and say rescale it, so for example, so that it appeared between -10 and -1. Yes?
Is this where you want to rescale it so that it has a higher value so that you have space underneath?
Sorry, say the question again?
Is this where you want it to rescale the traces so that it starts at a higher value so that you can put the mean and standard deviation?
Yeah, so for example, we could move the traces up. So right now, the first neuron starts at 1, and the 50th neuron is at 50. And we could move them up so that they start at 100. Or we could move this down so that it starts below that. I'm suggesting we move it down, but either would work, right? We just want to visually separate. And I'm saying not only do we want to move it down, but we might want to scale it so that we can choose, what fraction of the screen is it going to take up? Is it going to be as big as the number of traces? Is it going to be smaller? So let's change our plotting function here. Let's give it some optional arguments. Let's give it a desired minimum and a desired maximum. So who here does not remember how these optional keyword arguments work? Yeah, most of you seem to remember some of it. Okay, so you guys will remember that if we call the function without having specified the value of the argument, it takes on whatever value we wrote here, and if we call it specifying it, then it takes on whatever value we specify. And actually say, instead of nothing and nothing, which is a little more complicated, say that we wanted the default to rescale between 0 and 1. So what we want is our entire plot of the mean plus minus the standard deviation, its minimum to be at 0, and its maximum to be at 1. And we can specify whatever we want. Right? So we're doing this as arguments, so that later if we decide, oh, you know what, I want it between -10 and -5, we can just call it with those values. So we could say, we compute the mean, we compute the standard deviation, and then we could rescale the mean to lie between 0 and 1. Yes?
You always have to have a set value and have optional arguments in the new call.
Yeah. So the trick that I was going to do, say you can write nothing. And so then, for example, you can test for whether its value was nothing in case you want, if you want to detect, here's what I'm trying to say, sorry. So that we write it like this. And now say that execution has gotten to line 63. At line 63, I can't tell the difference between the user didn't put something in for mn versus the user put in 0. So a trick that you could use is write this, and then you can tell the difference between they put something in or they didn't put anything in. You can actually, this is a valid command. Right. And then you can write code for whatever you want in case they didn't write anything. Okay, but for now, let's do it 0. So let's say that we rescale the mean. So rescaling the mean will be great. It'll put it where we want it. And I shouldn't write 0 and 1. I should write mn and mx so that it follows the parameters of the function, right? So the user can control the rescaling. But then what should we rescale the standard deviation to? And what should we rescale? We wanted to rescale all three of them. We wanted the mean plus the standard deviation to reach a maximum of 1. And we wanted the mean minus the standard deviation to reach a minimum of 0. So let's look at these vectors. Let's do this. Let's say that our matrix A is the same as FR1. And now I'm going to compute these mu and SD vectors. I'm just copy pasting what we had before so that I've got them here on the console. In mu, it's a column vector, and SD is a column vector. So one thing that we could do is stack them all together as different columns of a matrix. So if we want to put column vectors together, what do we need to separate them with? When you're writing say a matrix or a vector, remember commas means it's going to be a vector, semicolons separates rows. What separates columns? Anybody take a guess? I'm writing a vector. I would like the vector to be one row and the columns 1, 3, and 2. I'd like it to be a vector like that. What could I write in Julia? X equals what? Spaces separate columns. Right? So commas means it's going to be a vector, doesn't really have rows or columns. Semicolons separate the rows. Spaces separate the columns. So what if we took the mean minus the standard deviation, and the mean plus the standard deviation. And so we've taken 3 columns, right, and we're putting them all together. And that makes one big matrix that has the 3 columns and has all of them in it. Let's call that M. And now we can rescale M. Say that we want it between -10 and -5. There again we have our 3 columns. We've rescaled the entire matrix, right? So we looked at values from across the entire matrix. And let's call MS, let's say that that's the rescaled M. So here, how do we pull out of MS the rescaled M, the mean minus the standard deviation, the mean, and the mean plus the standard deviation? Because we wanted to plot them, those 3, and we wanted to plot them with different line thicknesses. So let's look at how we made the original matrix. In the original matrix, the first column is the mean minus the standard deviation. The second column was the mean, and the last column was the mean plus the standard deviation. So in the rescaled matrix, how do I get, say, the mean? Exactly. In the rescaled matrix, the second column will correspond to the rescaled mean. The first column will correspond to the rescaled mean minus standard deviation. The third column will correspond to mean plus standard deviation. So let's do that here. Let's take our rescaled matrix, and what we're going to do is we're going to rescale this. We take the mean minus the standard deviation, the mean plus the standard deviation. And we want to rescale that whole thing between the desired minimum and the desired maximum. And now what we plot, for the mean, we plot the second column. You guys will remember, rows, then columns. Colon means give me the entire row. Second column. For the mean plus the standard deviation is the third column. Here it is right here, third column. And for the mean minus the standard deviation, it's the first column. Here it is, right here. Okay. So let's see if that works. Let's clear the plot. And now let's plot that, FR1. And now we've added these mean, minimum, and maximum, right? We can tell it where we want. So if we don't specify mn and mx, it should scale it between 0 and 1. Let's see if it works. So the claim is that the smallest value should be at 0, and the largest value should be at 1. Let's add something here. So sorry, it's Y label with an exclamation mark. So now you can see the numbers, and yeah, it rescaled it. You know, the smallest value is 0, the largest value of all 3 of those things, of mean minus standard deviation, mean plus standard deviation, it's all scaled to where we wanted it. Let's see if we can scale it to something else. Let's say that you wanted a mean of minus 200 and a maximum of minus 180. Oop. I should call it with the keyword, the minimum and the maximum. I forgot to clear the plot. Let me clear the plot and do that again. And yeah, now the minimum is minus 200 and the maximum is minus 180. Great. So now we can compute this and put it wherever the heck we want. So let's show our traces again. There are the traces. And now let's put the mean and the standard deviation. I guess I'm plotting FR2, so I should do it off FR2. And where would you guys like it? Tell me a minimum and a maximum to put it at. Anything of your choice. Yeah, anything that would look kind of nice on the screen.
0 to 20.
0 to 20. Sure, why not? 0 to 20. Maybe not the prettiest choice, right? Because then it overlaps with these other things. All right, so let's try again. Somebody said negative 15 to negative 5. Why not? Okay. You know, and you can play with it as you choose. And the thing that I want you to notice is we're using a bunch of things. We're using the rescale function, right? And now we're just using it, right? We've totally stopped worrying about whether the rescale function worked. Why do we do that? Because when we were writing the rescale function, we stopped there and debugged it completely there, and now we can just use it. And now that we can just use it, we've got a pretty flexible function, right? This plot mu SD, we can put this mean and standard deviation wherever we want. Okay, so we're almost done. Call it a day. I don't think we're going to be able to flip the axes and do the other one over here. Except there's one thing that I'll tell you. Okay, so suppose that we weren't trying to plot, to put it right here. So the plotting, you know, placing it exactly where we want takes a little care. But suppose that I now just wanted to plot the mean and the standard deviation here. Meaning, I want to average across time for each neuron. I don't want to average and take the standard deviation across neurons at each time point, but instead I want to take the average and standard deviation across time for each neuron. Is there something that we could do to this matrix FR2 to make it easy to do? We've got a function that almost does that. We wrote a function that did what we wanted to do along this direction. What could we do to use that function to compute things along this direction? It involves a single character operator that we used a little while ago, a few minutes ago. What do we use to flip rows and columns? Right. So if we flip the rows and columns of the matrix, then we can use our same function, and now it's going to be computing the mean and the standard deviation. You know, instead of doing it across the rows, it's going to be doing it across what the columns are. So we're not placing it relative to the individual traces, just because that's a little bit more complicated. We do the apostrophe, so now it's going to be this way. There's one last little thing. Remember, the length of t, oh, I think we put it in there, yeah. The length of t has to be as long as there are columns in this thing. We flipped the rows and columns, so now the number of columns in FR2 apostrophe is the same as the number of rows in the original matrix. So we could call it, say, like this. 1, 2, the number of rows in the original matrix. And that, remember, rows come first, column comes second, so that's why we use size brackets 1. And so that, in principle, I think it'll work. There we go. That one plots mean and standard deviation. FR2 is a little boring. It turns out that FR1 is a little more interesting. because it turns out, oh, let me clear the plot. Okay, last plot, and then you guys can go. It turns out that in that original data, FR1, the first half of the neurons had a higher average firing rate than the second half. All right, it's exactly 2:50. We've gone over matrices, for loops, functions. I hope you guys are okay. Rachel has something to say. Yes, thank you. The module exam is going to cover working with vectors and matrices, for loops, if-else statements, writing functions, and simple plotting. In other words, what we've just been doing.